Okay, so last time we looked at the problem of trying to find the instantaneous rate of change at a point. And the idea was to try to see, well, what happens when we attempt to use an average rate of change formula instead. And that's not really a bad place to start, to actually try to use the math that you already know how to use and apply it in a new situation and see what happens. And actually, that will be the right idea to actually get the answer that we're looking for, but we're going to need to be just a little bit more clever. So last time we saw that when we wanted to find if we had a function f of x equals 3.2x squared, and I want to find the average rate of change, which was given by this formula here, between the points 3 and 3.5, we actually show that that was 20.8. Just to recap, you can find what f of 3.5 is by basically plugging in 3.5 into the equation. And if you do so, you'll get 39.2. And then also if you plug in 3 in for x into this equation, you'll get 28.8. And all we need to do here is we need to basically have the change in x and the change in y. So take the change in y over the change in x, get this. And what we actually ended up getting was we ended up getting this nice graph over here. So remember, if this is 3 and this is 3.5, and actually it might be a little bit hard to see and do the scale of the graph, but we know that the y value over here has to be about 39.2 here, and then for the second point down here, it's going to be 20.8. So that means that the slope of a line, because all we're doing is we're finding the slope of a line through 2 points, is going to be equal to, sorry, that shouldn't be 20.8, that should be 28.8. But the slope will be 20.8. So that will be basically our answer here. Okay, when we tried to do the same thing using the same formula to try to find the average rate of change between the same point, we run into this issue. We run into this issue that we end up with something along the lines of 0 over 0. And that is where our problem began last time. So the strategy that we're actually going to employ here is that instead of actually trying to find an average rate of change or an instantaneous rate of change by applying the average rate of change at a single point, the idea is to maybe look at an approximation. So right here I have graphed in Desmos 2 points, and we have a line that's going through them, and we have our function right there, which is the red curve. And what you'll notice is that as I bring, so we've got a point fixed here at 3, but as I bring that point closer and closer to 3, you actually get closer and closer to a tangent line. So maybe we can actually do an approximation method where we bring our value between the 2 points really close to each other, and then that will give us what we think the instantaneous rate of change should be. So now we're going to actually try to employ that strategy of making smaller and smaller intervals. So again, we already found a couple times that the average rate of change of this function here from 3 to 3.5 is 20.8. And I think to kind of see what we're going to do in these next several computations, I want to consider a number line here. So I'm going to exaggerate, where certain values are to kind of try to make some room for this. But if I imagine that 3 is here, and I imagine that 3.5 is here, okay, and I want to choose a smaller interval like we showed in the graph in Desmos, I want to choose a point between 3 and 3.5. And it doesn't matter what point I choose, but for the purposes of our example, we're going to actually choose 3.1. So I know that 3.1, realistically speaking, is probably around right here, but just for illustration purposes, I'm going to put 3.1 over here. And now I want to find the average rate of change of this function. Again, this is just the x-axis. Remember that the function itself, in terms of a y-axis, is over here, and we've got, some sort of curve that, looks something like that up here. But that's going to be too cumbersome to deal with. But if we find the slope, and again, we're going to use the same formula, from 3 to 3.1, we're actually going to get 19.52. So just notice how these values change. We started at 20.8, and then we went to 19.52. And now if we do the same thing from 3 to 3.01, again, I'm suppressing all of the computation here. And again, the computation really is not particularly important. I mean, as long as you can do one average rate of change problem, you should be able to do others. Just make sure that you're careful in your substitutions. If you use a calculator, make sure you put parentheses in both the numerator and the denominator as you're doing this, and that you don't forget the squared like I did up there. And everything should be okay. But if you do this, you'll get 19.232. So again, 3.01. Again, it's not halfway between. It's actually a tenth of the way. It's like really close to 3. That's going to be a little bit smaller. And then I can choose a number that's even a little bit smaller, 3.001. And the point here is that as the interval gets smaller and smaller and smaller, you're actually going to get this tendency. Notice that we started at 20.8 and we went to 19.52 and 19.23. So those are decreasing numbers. Again, that's not the y values. Those are the slopes. And it's also important when you deal with patterns like this not to just consider a single side of 3, because notice we're choosing intervals here that are only to the right of 3, but we also want to consider values over here to the left of 3. So I might want to also consider, 2.9. And, 2 and again, these are not to scale, but 2.99. And we're going to do the same thing. So we're going to evaluate from 2.9 to 3, calculate that average rate of change. We get 18.88. And we're going to do the same thing for 2.99 and 2.999. And again, just look at the tendency. So these values are actually decreasing. So these values here are decreasing. And then these ones, I know that the arrow is going downwards, but these ones are increasing. And the point here is that as you get really, really close to 3, 3, remember that if I do 3, 3, I get that 0 over 0. But if I choose values that are really close to 3, we're actually going to get... We're not getting something that's undefined. We actually get what we think the instantaneous rate of change is. And it turns out that if you actually use more rigorous calculus methods, the instantaneous rate of change will be 19.2. So just the key here is not the computation, but the trend. Okay? And that's the strategy of looking at what happens as you get closer and closer to a particular value. And in the next section, we're going to define what that means. It's actually called a limit, and we'll see how that kind of becomes a calculus tool that helps us solve problems like these. But just to kind of reiterate what I was talking about now that we've actually done a couple of computations, again, the idea is that we're considering now the slope of this line, and the idea is that as that interval gets smaller and smaller and smaller, you get the slope of a tangent line. Notice right at the point, it's not showing a slope because it's undefined, but I can also choose points on the other side. And it's almost like if I do this quick enough, you kind of can anticipate what that value should be. So again, next time what we're going to look at is, how do we formalize the notion of being close to a value, but not exactly at that value, to kind of help us solve problems like the instantaneous rate of change problem. So next time, what we want to do is we want to formalize this process. And we're going to do so by defining something that is known as a limit. So I'll see you guys next time. Take care.